7.4 Lesson 2, Deriving the Definition of Arc Length. Our objective for today is you will understand how the calculus concepts listed below are used to derive the definition of arc length. And the main steps in our derivation are the steps that are highlighted. We actually start with the precalculus step, which will give us an approximation for the arc length. And then we start using calculus. We begin by forming a Riemann sum, which would be the sum of lengths of several line segments. And then we take the limit of that Riemann sum, and if that limit exists, we will get a definite integral. So those are the main steps that you will see in the derivation today. So you need to remember these calculus concepts. What's a Riemann sum? What is the definition of a definite integral? It is, in fact, the limit of a Riemann sum. And as a part of understanding a Riemann sum, you have to understand what a partition is, what we mean by the norm of the partition, and as a part of understanding the definition of a definite integral is the limit of a Riemann sum if that limit exists. And how do you know if the limit will exist? If the function that forms the integrand is continuous, there is a theorem in calculus that tells us that that is enough to guarantee the existence of this limit of a Riemann sum, and therefore we will have that definite integral. As a part of the process for deriving the definition of arc length, somewhere in the process we are using the mean value theorem to make a substitution. And when we use the mean value theorem, we are relying on a hypothesis of the definition of arc length. Hypothesis is like a prerequisite condition that is needed for you to be able to use the definition of arc length. And the reason why that is there is because it was used in the derivation of the definition. And then as a part of the derivation, we're also relying on this particular concept: differentiability implies continuity. So what we'd like to do is we'd like to begin our lesson. So this is the outline of the lesson. 1, review of prerequisites. So we're going to do a review of these calculus concepts. And then we will go ahead and take a look at the derivation of the definition of arc length. And as we look at the derivation, we will refer to these concepts that we will review first. So now we will go ahead and do number 1, review of calculus concepts. And let's do it this way, where we will start with the 3 that are down here, and then we will take a look at the ones that are above that. So we will begin with differentiability implies continuity. Differentiability implies continuity. That's Theorem 2.1 from your textbook, and it states simply that if a function f is differentiable at x is equal to c, then it is also continuous at x is equal to c. So one thing to note about this particular theorem is that the converse is not true. You could have a function that's continuous at a point, but not necessarily differentiable at that point. However, if a function is differentiable at a point, it must be continuous at that point. So the converse is not true, but this conditional statement is true. It is a theorem. There is a proof of it in your textbook, but we won't look at that now. So if a function is differentiable on an interval of x values, it is also going to be continuous at each of those x values from the interval. Also used in the derivation of the definition of arc length is the mean value theorem. And here's the statement of the mean value theorem from your textbook. It is Theorem 3.4, and it is stated as a conditional statement. You have if, then. So we have hypotheses, and if the hypotheses are satisfied, the conclusion must follow. And the hypotheses of the mean value theorem are that you have a function f that is continuous on the closed interval a to b, so that's one hypothesis. And the other hypothesis is that this function f is differentiable on the open interval from a to b. So if those two conditions are satisfied, the mean value theorem guarantees the existence of a particular number c between x is equal to a and x is equal to b, such that the derivative of the function f at c will be equal to this difference quotient. Let's see if we can interpret the mean value theorem graphically. So this is a part of our review of calculus AB concepts. So here we have a diagram to help us understand the mean value theorem. So we will begin by looking at the graph that's shown. That's the graph of the function f. And you will notice that the graph that is shown here in this diagram is continuous from x is equal to a to x is equal to b. There is no break in the graph. There are no discontinuities, jump discontinuities. There are no step discontinuities. There are no removable, non-removable discontinuities. The function's graph can be drawn without lifting your pen as we go from point A to point B. So we do have a function that's continuous on the closed interval from A to B, and the curve here represents a function that is also differentiable on the open interval from A to B. And one thing that you might remember from calculus AB about differentiability of a function and how that relates to the graph of the function is that if the graph of a function has a sharp corner at a particular x value, the function is not differentiable at that x value where the graph has a sharp corner or a cusp. But you don't see that here. The graph of the function f is smooth, implying that the function f, the graph represents a function that is differentiable on the open interval from a to b. Those are the two conditions required by the hypotheses of the mean value theorem. So if that happens, the mean value theorem guarantees the existence of at least one value c between x is equal to a and x is equal to b. So the mean value theorem states that there has to be at least one x value c between a and b such that this must be true. And what is this stating? So this equation on the right side has a difference quotient. And if you look at that difference quotient, it is simply the change in the y coordinates. You've got f of b minus f of a, so you're subtracting the y coordinates and then dividing that by the difference in the x coordinates, b minus a. So that's what you have. In other words, the right side of this equation is telling you the slope of a line passing through these two endpoints. We'll call them points maybe A and B, uppercase A and uppercase B. So the right side of that equation is giving you the slope of what we call the secant line passing through the two endpoints of the interval. So let me go ahead and trace that secant line using red ink. So the mean value theorem states if the two hypotheses are satisfied, there has to be at least one c value between x is equal to a and x is equal to b at which the derivative of the function evaluated at c will equal the slope of that secant line that we just traced in red. So there has to be at least one x value between a and b at which the derivative of the function, which represents slopes of tangent lines. So in other words, there has to be at least one tangent line to the graph of f on the interval from a to b at which the slope of the tangent line will be equal to the slope of the secant line passing through the two endpoints of the interval. So that's what the mean value theorem guarantees. So this is the graphical interpretation of the mean value theorem, that there is at least one tangent line having the same slope as the secant line passing through the two endpoints. Now, you can also interpret the mean value theorem in the context of a word problem. The right side of the equation would give you an average rate of change, and the left side of the equation would give you an instantaneous rate of change. So in other words, the mean value theorem, if the hypotheses are satisfied, would guarantee for a word problem that there is at least one time at which the instantaneous rate of change of one quantity with respect to another is equal to the average rate of change of that quantity with respect to time on a time interval from x is equal to a to x is equal to b. So we're going to use this, and you'll see how we use this when we look at the derivation. Then we have Theorem 4.4 from your textbook, Continuity Implies Integrability. If a function f is continuous on the closed interval from a to b, then that function is integrable on the closed interval from a to b. And we're going to use this theorem in conjunction with the definition of a definite integral. Because in the definition of a definite integral is defined as the limit of a Riemann sum if that limit exists. So how will you know if the limit exists? If the integrand is a continuous function, by this theorem, the limit must exist because it is telling us that the function would be integrable. So that's how this comes in our derivation. So we're still doing our review of calculus concepts, and we've taken care of these three things down here. And now we're going to look at what a Riemann sum is. And in talking about a Riemann sum, you look at vocabulary. What is a partition? What do we mean by the norm of a partition? And then we will look at the limit of a Riemann sum, which will give us a definite integral. That's a definition. And then we will be ready to look at our derivation. And as we look at our derivation, we will be referring to these concepts that we're going over now. What is a Riemann sum? We will begin just by looking here, and we will say that a Riemann sum is the sum of products. If you look at this sum that I circled in red, you will see that it is a product between a function evaluated at some input and delta x sub I. And what is delta x sub I? It is the width of the ith subinterval. So what are we talking about when we say the ith subinterval? Let's get into that by looking at the definition of a Riemann sum. So you have a function f, and that function f is the function that you see here. Let f be defined on the closed interval from a to b, and then you have this symbol. It represents a partition of the closed interval from a to b given by what you see here. So let me explain what that means. All that means is this. You have an interval of x values from x is equal to a to x is equal to b. For example, a could be 3 and b could be 6. So how will you divide that interval into subintervals? Any way you want, really, any way you want. You can divide it into a number of subintervals as you please. You can have 2 subintervals and they could be the same width. You can have 2 subintervals and they could be different widths. So for example, if you have 2 subintervals and they are the same width, I'm going to have one subinterval from 3 to 4.5 and another subinterval from 4.5 to 6. Each subinterval would have a width of 1.5 units. 3 to 4.5 is 1.5, and 4.5 to 6 is 1.5. Or I could have two subintervals and they could be different widths. Maybe one subinterval is from 3 to 4, and another subinterval is from 4 to 6. So now one of my subintervals is wider than the other. So you can have a partition any way you please with any number of subintervals. They could be different widths, they could be the same width. So this symbol here, which we can read as delta, it represents a partition of the closed interval from A to B, given, as you see here, this is just a general way of expressing what I stated in words, that you can divide your interval from A to B any way you'd like. So you can, but however you divide it, A, which is the left endpoint of your interval, will be denoted by x naught, and B, which is the right endpoint of your interval, will be denoted by x sub n. So for the example that I gave here, my partition points will be x naught will be the left endpoint, which will be 3, x sub 1 will be 4, and x sub 2 will be 6. And what I have here are two subintervals of unequal widths. Okay, so n here represents the number of subintervals you have. So in my diagram, I have two subintervals. And you see here where delta x sub I is the width of the ith subinterval. What does that mean? So if I look at delta x sub 1, it is going to be equal to 4 minus 3. And the width of my first subinterval will be 1. If I look at delta x sub 2, it's going to be 6 minus 4. And the width of my second subinterval will be 2. So delta x sub I represents the width of the ith subinterval. Now, the next part of the definition of a Riemann sum states if C sub I is any point in the ith subinterval. In other words, I'm talking about C sub 1, and C sub 1, let me make some space up here. C sub 1 could be any point from the first subinterval. And my first subinterval is from x is equal to 3 to x is equal to 4. So C sub 1 could be any value between 3 and 4. So, and then C sub 2, in my example here, could be any value between 4 and 6. Any value between 4 and 6. So we have C sub 1 being an x value from the first subinterval, and C sub 2 being an x value from the second subinterval. So C sub I is any point in the ith subinterval. Then this sum, which is the sum of a product, you have the function f evaluated at C sub I, which is, as we discussed, an x value from the ith subinterval, and it could be any x value from the ith subinterval, and the function f is evaluated at C sub I, and then you're multiplying that by the width of the ith subinterval. So, and then you have a product here, and you take the sum of these products from I is equal to 1 to I is equal to n. So whatever function I have, I could do this, and I could get a Riemann sum, and again you have here C sub I is between x sub I minus 1 and x sub I. This is called a Riemann sum for the Riemann sum of the function f for the partition delta. And you can read here, the width of the largest subinterval of a partition is called the norm of the partition. So in my example, the norm of the partition for me is going to be 2. The width of the larger subinterval from 4 to 6 is 2. That is the norm of my partition. It is denoted by this symbol. So for my example, I would write that the norm of my partition is 2. And if every subinterval is of equal width, if every subinterval is of equal width, we say we have a regular partition. We don't have that in my example. So you use this idea in calculus AB to approximate the area of a region under a curve. And I'll show you how you did that before going on to the next part of our review, which is looking at the definition of a definite integral. So let's take a look at this problem that you had in calculus AB. You have the function f of x is equal to 4 minus x squared, and you see the graph of the function here on the interval from x is equal to 0 to x is equal to 2. And you want to find the area between the graph of the function and the x-axis, between x is equal to 0 and x is equal to 2. But of course, you don't know a formula from geometry that would allow you to do that, because the boundary that you see in red, the graph of the function f, it's not a line segment, it's a curve. So the region that you have is not quite a triangle. So what did you do before you could find the exact area? You found an approximation for the area. And one way you can find the approximation is to take the interval from x is equal to 0 to x is equal to 2 and divide it into maybe 2 subintervals. So your partition would be as follows. So here you have x is equal to 0, here you have x is equal to 2. So you have a is equal to 0 and b is equal to 2. So you're going to have x naught is equal to 0. You can have x sub 1 is equal to 1, and you can have x sub 2 is equal to 2. So you have a regular partition. In other words, the 2 subintervals in my partition have the same widths, and the width of each subinterval is 1 unit. And you can see that c sub 1 could be any value between 0 and 1, and c sub 2 could be any value between 1 and 2. So I can choose c sub 1 to be any value between 0 and 1, and I can choose c sub 2 to be any value between 1 and 2. So let's say I choose c sub 1 to be the left endpoint, and I choose c sub 2 also to be the left endpoint. And now I'm going to evaluate my function f at the chosen values of c sub I. So I will evaluate my function f at x is equal to 0. So 4 minus 0 squared is 4. And I will evaluate my function f at x is equal to 1. So I have 4 minus 1 squared. 4 minus 1 is 3. And then, according to this definition of a Riemann sum, which is right here, you have the sum of a product, where one factor is the function f evaluated at c sub I, and the other factor is the width of the ith subinterval. So the width of the first subinterval is 1 minus 0, which is 1. The width of the second subinterval is 2 minus 1, which is also 1. But in the context of this problem from calculus AB, the width of each subinterval tells you the width of a rectangle. And let me draw a rectangle here on the first subinterval whose height will be 4 units and whose width is 1 unit. And let me draw a rectangle on my second subinterval whose height will be 3 units and whose width will be 1 unit. So what is this Riemann sum giving us in the context of this problem from Calculus AB. The first rectangle gives us an area because we're doing height times width to get the area of the first rectangle. And then we're doing height times width to get the area of the second rectangle. So this Riemann sum in the context of the problem that we just looked at is giving us the sum of the areas of these two rectangles, and I would go from 1 to 2. So that's what a Riemann sum is. Now, a Riemann sum can be used in different contexts. In Calculus AB, you used a Riemann sum, for example, to find a sum of areas of rectangles. Today, we're actually going to use a Riemann sum to find the sum of lengths of line segments. And you'll see that when we look at the derivation. So when you did this, this was the beginning of your process in coming up with a definite integral to give you the exact area of the region under the curve. What you have here is an approximation. So how do you go from an approximation to the actual exact area under the curve? You have to use the limit of a Riemann sum, which would give us a definite integral. Conceptually, the idea is simple. If you have more rectangles, we expect that the approximation will be more accurate. So let's just take this idea to the extreme and increase the number of rectangles on and on and on without end. A more mathematically precise way of stating that is, let's make the width of each subinterval approach 0. So we're going to make the norm of the partition approach 0. So here you can see that the norm of my partition is 1 because the width of the largest subinterval is 1. If we make the width of the largest subinterval approach 0, that means the number of rectangles will approach infinity, and we expect that the more rectangles we have, the better our approximation will be. And we're going to say, let's take the limit of this Riemann sum as the norm of the partition approaches 0. In other words, as n goes to infinity, and the more rectangles we have, the better approximation we should have for area. And we're going to say, by definition, the limit of this Riemann sum as the norm of the partition goes to infinity will give us the exact area. So that's what we did in Calculus AB, and today we're going to go through that same process, but apply it to a different context for finding arc length. So now we get to the definition of a definite integral. So if you have a function f defined on the closed interval from a to b, and the limit, and look at this limit. Look at this part here. This is a Riemann sum. And the limit of this Riemann sum as the norm of the partition approaches 0, if this limit exists, then we say the function f is integrable on the closed interval from a to b, and the limit that you see here will be represented by this notation, which is, of course, the notation for a definite integral. How do you know if this limit will exist? Continuity implies integrability. If a function f is continuous on the closed interval from a to b, then f is integrable on the closed interval from a to b. So continuity implies integrability. And if that limit, so if you have a function f that's continuous, we know this limit will exist by this theorem. So that limit can be represented by a definite integral. This limit is called the definite integral of the function f from a to b. The number a is the lower limit of integration. The number b is the upper limit of integration. So what is a definite integral? It is the limit of a Riemann sum as the norm of the partition approaches 0, in the context of our area problem from calculus AB, we're going to take the limit of a Riemann sum as the norm of the partition approaches 0, which means the number of rectangles will be approaching infinity. And you can expect that as we have more and more rectangles, the approximation will become better and better. And if you take the limit of the Riemann sum as the norm of the partition goes to 0, then you will, by definition, have the exact area of this region, which will be represented by a definite integral. And of course, later on, you learned how to evaluate a definite integral by using the fundamental theorem of calculus. So now we have reviewed the calculus concepts that we need to understand the derivation of the definition of arc length. And that is our objective, and we're ready to look at it. You will understand how the calculus concepts listed below are used to derive the definition of arc length. But of course, we actually have to begin with precalculus, just like we did in calculus AB. In calculus AB, the precalculus that you began with was the formula for the area of a rectangle. You do height times width. That was the precalculus that you began with for this problem from calculus AB. The precalculus that we will begin with today to come up with our approximation for arc length is the distance formula. So for the derivation that we're about to go over, these are the three main things that you need to be aware of. We begin with our precalculus distance formula, and then we apply that distance formula to find the lengths of several line segments. And when we add the lengths of those several line segments together, we would get a Riemann sum, and that sum will give us an approximation for the length of the arc. And then we take the limit of that Riemann sum as the norm of the partition approaches 0, and that limit, if it exists, will give us a definite integral, which will give us the exact arc length. And of course, that definite integral is the definition of arc length. So that's what we're going to look at now. At the end of our derivation, this is what we will come up with, which is, of course, what we used yesterday to do our homework problems, the definition of arc length. But I want to call your attention to one thing before we get started with the derivation. If you look at this definition, there is a prerequisite condition that your function f must satisfy. It states here, let the function given by y is equal to f of x represent a smooth curve on the interval from x is equal to a to x is equal to b. Why is this necessary? We actually use this in the derivation to come up with our definite integral. It is a condition that we need because it is something that we're using in the derivation to come up with this definite integral. So that's why it's there. So y is equal to f of x represents a smooth curve on the interval from a to b. The arc length of f between a and b is given by the definite integral from x is equal to a to x is equal to b of the square root of 1 plus the square of the derivative of f, and you are integrating with respect to x. And similarly, for a smooth curve given by x is equal to g of y, the arc length of g between c and d is given by the same definite integral. We just have the limits of integration for y because we're integrating with respect to y, and we have x as a function of y, and we're finding dx dy and squaring it. So we begin with our first step, which is to come up with an approximation for the length, for the arc length that we're interested to find. So let's say we have a curve, such as the one that you see here, and let's say we want to find the length of this curve from x is equal to a to x is equal to b, as I'm about to trace in green. So if you wanted to find the length of this arc, you can approximate that by using several line segments. So for example, you can approximate the length of this arc by using maybe 3 line segments. So let's say we have one line segment from, we'll call this x naught, y naught, to x sub 1, y sub 1. So there's one line segment. And let's say we have another line segment from x sub 1, y sub 1 to x sub 2, y sub 2. And let's say we have a third line segment from x sub 2, y sub 2 to x sub 3, y sub 3. So we have 3 line segments. So how do you find the length of each line segment? Well, we're going to say d sub 1 is equal to, if you look at the distance formula, it says subtract the x coordinates of the 2 endpoints. So if I'm finding the length of the first line segment, which is L sub 1 here, I would do x sub 1 minus x naught, and I would square it, plus y sub 1 minus y naught, and I would square it. So that's the length of my first line segment. I'll call that d sub 1. d sub 2 would be the length of my second line segment. So I would subtract the x coordinates of the 2 endpoints. I will have x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. And the length of the third line segment will be x sub 3 minus x sub 2, and you're going to square that, and you're going to have y sub 3 minus y sub 2, and you're going to square it. Again, all you're doing is you're subtracting the x coordinates of the 2 endpoints, x sub 3 minus x sub 2, and then squaring it plus the difference in the y coordinates of the 2 endpoints, y sub 3 minus y sub 2, and we're going to square that. So this is going to give you the length of each of these 3 line segments that you see in blue, gold, and black, and when you add them together, you will get a sum of these 3 lengths, which will give you an approximation for the arc length that we're interested in. And the idea is, the more line segments you use, the better your approximation should be. So if you look at the way I've drawn this out in particular, you will see that my first subinterval goes from x is equal to 0 on my diagram to x is equal to 3, and my second subinterval goes from x is equal to 3 to x is equal to 7, and my third subinterval goes from x is equal to 7 to x is equal to 10. So the width of my first subinterval will be x sub 1 minus x naught, or 3 minus 0, which will be 3. The width of my second subinterval will be x sub 2 minus x sub 1, or 7 minus 3, which will be 4. And the width of my third subinterval will be x sub 3 minus x sub 2, and that's going to be 10 minus 7, which will be 3. So the norm of my partition is going to be 4. So the idea is, if you wanted to have a better approximation than what you would get from the segments that I drew, you can narrow the width of each subinterval. Basically, you want to have maybe one more subinterval, and the width of the largest subinterval could be maybe 3 instead of 4. Or you can have 10 subintervals, and you could have a regular partition, and the width of each subinterval would be 1. Imagine having 10 subintervals. Or yesterday I did just 5, and it was a regular partition, and that would give you a better approximation than this. So the next step in our process is to represent the sum of the lengths of n line segments, and then we have to manipulate it algebraically to make it a Riemann sum. You can have a sum, but it's not a Riemann sum unless it is the sum of products. So we're going to have a sum first, and then we have to manipulate that sum algebraically to turn it into the form of a Riemann sum so that we have a sum of products. So that's what we're going to do next. But before we do that, I'd like to call your attention to one thing, and that is we can generalize what we're doing here. So we can write delta x sub I is equal to x sub I minus x sub I minus 1. You can see, for example, delta x sub 1 is x sub 1 minus x naught. Delta x sub 2 is x sub 2 minus x sub 1. Delta x sub 3 is x sub 3 minus x sub 2. And of course, 2 is 1 less than 3. So you have delta x sub I minus delta x sub I minus 1. And also, you can do the same thing for the y coordinates. You can write delta y sub I is equal to y sub I minus y sub I minus 1. And you will see this as a part of our derivation, so that's where that comes from. So now we've done precalculus with our distance formula. We're going to write a sum, and then we have to do some algebraic manipulation so that we will have a Riemann sum. A Riemann sum is not just any sum, it is the sum of a product. So we want to have a Riemann sum. Why do we need a Riemann sum to give us our approximation? Because once we have our Riemann sum, we'd like to take the limit of our Riemann sum and use the definition of a definite integral, and that would give us a definite integral, which will give us the exact arc length. So this derivation is, of course, in your textbook, but I'm explaining it so that you can understand it. And this is from the first page of section 7.4 in your textbook. So let's read that. So we begin by saying a rectifiable curve is one that has a finite arc length. You will see that a sufficient condition for the graph of a function f to be rectifiable between 2 points is that f prime be continuous on the closed interval from a to b. Why do we require this? Because we're actually going to use this as a part of the derivation. Such a function is continuously differentiable on the closed interval from a to b, and its graph on the closed interval from a to b is a smooth curve. And that is why in the definition of arc length, that prerequisite is stated. You have a function whose graph is a smooth curve. Then if you can find the length of that arc between x is equal to a and x is equal to b by using this definite integral. So now we have the following. Consider a function y is equal to f of x that is continuously differentiable. We talked about why we're requiring that on the closed interval from a to b. You can approximate the graph of f by n line segments, as you just saw in my demonstration with my particular example with 3 line segments, whose endpoints are determined by the partition x naught is equal to a and x sub n is equal to b. So now let's continue reading. And you will see this, delta x sub I is equal to x sub I minus x sub I minus 1, and delta y sub I is equal to y sub I minus y sub I minus 1. And of course, we just talked about that and why that is the case and what that means. So now what we're going to do is we're going to add the lengths of n line segments, and that would give us an approximation for the arc length. It would give us a sum, and then we have to do some algebraic manipulation to make it a Riemann sum. In other words, we would have the sum of products. So when you take a look at what you see here in this line, you can see that you have summation notation where the index I goes from 1 to n. And then what you see here is, of course, the distance formula. And let's take it in the context of what we had done with our demonstration using 3 line segments. If you were to do that, then you would have from I is equal to 1 to 3, and you would have this formula, the distance formula, delta x sub I. By the way, this is delta x sub I. It's the width of the ith subinterval. And then this is delta y sub I, the difference in y coordinates on the ith subinterval. So if you were to substitute I is equal to 1, I is equal to 2, and I is equal to 3, then what would you get? For I is equal to 1, you would get this. For I is equal to 2, you would get this. And for I is equal to 3, you would get this. And this sum would represent the sum of the lengths of those 3 line segments. The 3 line segments that you see here in blue, in gold, and in black. What you have here is just more general. Why stop at 3 when you can have more? Maybe you want to have a better approximation, so maybe you want to have 5 or 10 or whatever. So we have n instead of 3. And what is this? This is delta x sub I, the width of the ith subinterval. So we make that substitution to get the next line, which is right here. So we substitute for this delta x sub I, and we substitute for this quantity delta y sub I to get the next line. So we have a sum, but it is not a Riemann sum, because a Riemann sum is the sum of a product. We don't have a product right now. We just have the square root of delta x sub I squared plus delta y sub I squared. So the next thing that we need to do is we need to do some algebraic manipulation to turn this sum into a Riemann sum, so that we will have the sum of products. So how do we do that? Here's what we're going to do. You're going to do this algebraic manipulation that you see here. And to convince yourself that we're not changing anything, let's take a look at it in closer detail. What is it that we're doing to go from this step to the next step? The only thing that seems different is what I'm circling in red here. But is that really different? It's not. It's really exactly the same as what you had the previous line. Because take a look at what we're adding, or what we have. We have delta y sub I over delta x sub I squared times delta x sub I squared. So if you distribute the square to each of these, then you will have delta y sub I squared over delta x sub I squared. And then of course you have this delta x sub I squared. So when you look at it that way, you can see that these two common factors will cancel, and you're just left with this, which is exactly what you had in the previous line. So we are not making any changes. It is algebraically equivalent. So that's our algebraic manipulation. So why do we do this? Because we want to have a Riemann sum. So how do we go from this line to the next line? Well, the next line represents a Riemann sum because you have the sum of a product. And here's our product. You have one factor circled in red and another factor circled in green. And more importantly, you want your product to have delta x sub I, because when you take the limit of the Riemann sum, this is the part that will become dx in your definite integral. So you want your Riemann sum so that one of the factors is delta x sub I. And that is why we're going through all of this. So how do we go from this line to the next line? Well, you have this property. Here's what you're doing. Let me show you here. So you have from I is equal to 1 to n, and you have the square root of delta x sub I squared plus delta y sub I over delta x sub I squared times delta x sub I squared. So what happens is this. In the radicand, you have two terms. They have a common factor of delta x sub I squared. So I can factor that out from each term. So let's factor that out from each term. I'll write it on the right side. And from the first term, you'd be left with 1. And from the second term, you'd be left with, if you factor this quantity out of the second term, you'd be left with this quantity here, which is, of course, delta y sub I over delta x sub I squared. So that's the algebra that you're doing. And then, of course, you know that if you have the square root of a product, you can write that as a product of the square roots. So that's the next step. So when we do that, because now you have the square root of a product, here's the product, so you can write that as a product of the square roots. So you're going to have this and of course, here you have the square root of a quantity that is squared, so that's how you simplify this to just delta x sub I, and you have the other factor, which is what we have here. So now we have a Riemann sum. We have a Riemann sum, we have the sum of products, and one factor in our products is delta x sub I. We need that, because now we're going to take the limit of this Riemann sum as the norm of the partition approaches 0, and if that limit exists, it will give us our definite integral. So that's what you see here. This approximation appears to become better and better as the norm of the partition approaches 0. In other words, as the number of line segments approaches infinity. So the length of the graph is given by the limit of this Riemann sum as the norm of the partition approaches 0. But we're not quite where we want to be. We do need to make a substitution for this quantity, and the way we're going to make that substitution is by relying upon our hypothesis that f prime, the derivative of f, is continuous. In other words, it is defined at all x values on the interval from x is equal to a to x is equal to b. We're going to use that hypothesis along with the mean value theorem to make a substitution for this quantity, and then we will be able to finish. So now we look at this. So because f prime of x exists, and that's from our hypothesis that f prime is continuous on the closed interval from a to b, meaning it is defined at each x value on the interval from a to b, so it exists. So what does it mean if the function f is differentiable for each x on the interval from x sub I minus 1 to x sub I? In other words, on each subinterval of the interval from a to b. So remember, we're partitioning this into a number of subintervals. So if f prime exists for all x from x is equal to a to x is equal to b, then it must certainly exist for all x in each of its subintervals. So if f prime of x exists for each x in the subinterval, in the ith subinterval, this is delta x sub I, why can we use the mean value theorem? Because the mean value theorem has two hypotheses. If you have a function that is differentiable on the open interval from a to b, and we have that, the derivative exists, and differentiability implies continuity. So our function f must be continuous on the closed interval from a to b. So because of differentiability implying continuity, this condition by itself is enough for us to know that the hypotheses of the mean value theorem are satisfied, and therefore we can use the conclusion of the mean value theorem to write the following. So again, we have differentiability of our function on the open interval from a to b, and that implies continuity of the function, and we're looking at this particular interval, the ith subinterval of our partition. So the mean value theorem is applicable, and it would guarantee the existence of a particular x value in the ith subinterval. So c sub I is between x sub I and x sub I minus 1, such that, this is what the mean value theorem tells us, f prime of c sub I is equal to the function evaluated at the right endpoint of the interval, which would be x sub I, minus the function evaluated at the left endpoint of the interval, which would be x sub I minus 1, divided by x sub I minus x sub I minus 1. That's coming from the mean value theorem. So now, if you manipulate that, what do you get? What is this? This is a change in y. It is the same as writing y sub I minus y sub I minus 1. And of course, in the denominator, you have x sub I minus x sub I minus 1. So that's f prime of c sub I. And what is this? It is delta y sub I. And what is this? It is delta x sub I. So you can replace this particular quantity in our Riemann sum with f prime of c sub I because of the mean value theorem, and the mean value theorem is applicable because of the hypothesis that our function f is continuously differentiable on the closed interval from a to b, meaning that its derivative exists on the closed interval from a to b, which means the function f is continuous on the closed interval from a to b. So what did all of this allow us to do? It allows us to substitute this particular quantity here that I circled in red with f prime of c sub I. So this Riemann sum now can be written like this. So you have the arc length is equal to the limit of this Riemann sum, but now we're able to substitute for this quantity with f prime of c sub I. So this becomes f prime of c sub I squared. So you have the square root of 1 plus f prime of c sub I squared, and of course you have that delta x sub I. So what is this that we have here? What we have here is the limit of a Riemann sum as the norm of the partition approaches 0. That's what we have. So what is the limit of a Riemann sum as the norm of the partition approaches 0? It is a definite integral by the definition of a definite integral if this limit is known to exist. But how do we know that this limit exists? Continuity of the integrand implies integrability. So how do we know that this particular function here is continuous? We know from the hypothesis that since our function f is continuously differentiable, f prime is continuous on the closed interval from a to b. And 1, so look at this here. You have f prime of x, which we know to be continuous on the closed interval from a to b. We have the square of that. The squaring function is continuous. It's just f of x is equal to x squared. So you have a composition of f prime with the squaring function. So if you have a composition of two continuous functions, the composite function will be continuous. That's also something you learned in calculus AB. 1 is a constant function, which is everywhere continuous. So now you have a sum of two continuous functions, which is going to be continuous, also something that you learned in calculus AB. And then you have the square root function, which is continuous, and you have a composition of continuous functions, which is going to be continuous. So that's how we know, starting with the continuity of f prime, that the integrand will be continuous, and continuity implies continuity implies integrability. Continuity implies integrability, and because of that, we know this limit exists, and by definition, that limit is a definite integral. Again, what is a definite integral? If this limit exists, that's a definite integral. A definite integral is the limit of a Riemann sum as the norm of the partition approaches 0. And that's what we have here. And we know that limit will exist because we can analyze this particular function to be continuous, and continuity implies integrability. So there we have it. This is the definition of arc length. It represents the arc length of the function f between x is equal to a and x is equal to b. So we have derived the definition of arc length. And what you just saw is what we had outlined earlier. We began with our precalculus distance formula, and then we wrote a Riemann sum, which gives us an approximation for the arc length, and then we took the limit of that Riemann sum as the norm of the partition approaches 0, and by definition that gives us a definite integral, which gives us the exact arc length. So today we understood how the calculus concepts listed here are used to derive the definition of arc length.